Every major AI lab right now is racing to build the biggest context window possible. We already had 1 million context window, 2 million and now 12 million by Subquadratic. And the industry is cheering like this is the finish line. It's not. I'm going to show you why blindly scaling context windows could be one of the most expensive architectural mistakes in modern AI. And also the 3 technical realities that not many are talking about honestly. And at the end, the actual memory architecture that I think wins. Stay with me. Before we go deep, let me be clear about what this video is. This is not a bigger is bad argument. Larger context windows unlock genuinely powerful capabilities, and I'll show you exactly which ones. But I've designed AI systems that run in production, and the gap between impressive benchmark numbers and what actually holds up under real enterprise load is something I want to close for you today. So let's start with what a context window actually is, and more importantly, what it isn't. Think of the AI as a brilliant analyst you've brought into a meeting room. The context window is the table in front of them. Everything on that table, your question, your documents, your conversation history, your system instructions, has been converted into tokens. Now here's the mechanism that makes it all work. Every token compares itself to every other token to understand relationships and meaning. That's how the model figures out what's relevant to your question. Now, a critical distinction that is important to understand. This table gets completely cleared after every meeting. The model has no persistent memory between sessions. No recall. No continuity. Every session, it rereads everything from scratch. That's not a minor implementation detail. That's the core architectural tension we're going to spend this video unpacking. And it has 3 expensive consequences. Why bigger windows are genuinely exciting. Now, to be fair, and I want to be very fair here, larger context windows have unlocked things that genuinely surprised me. Analyzing entire codebases in one pass? Real. Maintaining coherence across multi-hour agent workflows? Real. Processing a company's full knowledge base as a single prompt? Happening now. Now, there is this company called Subquadratic just released SubQ, a model with a native 12 million token context window. We will discuss this in details later in the video. For now, they're using a new technique called Subquadratic Selective Attention, SSA, which directly attacks the efficiency problem I'm about to describe. That's real architectural progress. I'm not dismissing it. But, and this is a significant but, a bigger window doesn't fix the underlying memory problem. It changes the cost equation. And not always in your favor. Here's why. The 3 technical realities. Reality 1, compute scaling. The part everyone gets half right. You've probably heard that attention has quadratic complexity, O, and superscript 2. Double the context, quadruple the attention operations. At 1 million tokens, you're doing 1 trillion comparisons. That's true. But here's what most explanations get wrong, including ones I've seen from people who should know better. Attention isn't the only thing that scales. The feed-forward layers in a transformer, the parts doing the actual reasoning, scale linearly with context length. And for large models, 7 billion parameters and above, the feed-forward layers actually dominate compute cost until your context window exceeds roughly 50,000 tokens. Read that again. Below 50k tokens, you're mostly paying for the model's thinking, not its memory. The crossover happens around 50k tokens, which is exactly where most long context marketing claims start. So the quadratic argument is real, but it bites you later than most people say. Now, KV caching changes this further, and I need to address it directly because it's the most common pushback I get. Key value caching means that during a conversation, the model doesn't recompute attention from scratch for every single response. It caches the key and value matrices from previous tokens and reuses them. So mid-conversation, your inference cost is dramatically lower than the naive quadratic picture suggests. This is real. KV caching is standard in every production inference stack. But, and this is where it gets expensive, caching only helps within a session. Cold start. New user. Fresh session with 12 million tokens of company knowledge preloaded? That first token costs you the full quadratic hit. No cache to rescue you. And at 12 million tokens, even maintaining a warm KV cache has a memory footprint that will make your infrastructure team very uncomfortable. For enterprise deployments? A customer support system handling thousands of daily users, each with a cold start long context? The math gets painful very quickly. One more nuance. Even with caching, the memory bandwidth cost of loading a 12M token KV cache from HBM to compute units is non-trivial. At scale, that's not free either. Reality 2, context pollution and the lost in the middle problem. Here's the one that should alarm anyone building production RAG systems. In 2023, Liu et al. Published a paper called Lost in the Middle. I'll link it in the description. The finding was stark. LLMs perform significantly better when relevant information appears at the beginning or end of the context window. When you bury critical information in the middle of a long context, performance drops, measurably, consistently, across model sizes. Think about the implication. You give the model more information, and it gets worse at the task. Why? Because attention dilutes. Flood the context with irrelevant tokens and the signal-to-noise ratio collapses. The model's attention mechanism, designed to find relevance, gets overwhelmed by volume. I call this context pollution. And it gets worse as windows get bigger, not better, unless you're being very deliberate about what goes in. This isn't theoretical. I've seen this break real pipelines. A team loads a 200-page document into context because the window is big enough, and the model misses a critical clause that was on page 94. Bigger window. Worse answer. Real consequences. Reality 3. Latency, the silent killer for agentic AI. The third problem is the one that will quietly kill the agentic AI dream if we don't architect around it. Real-time autonomous agents, systems making decisions in live workflows, robotics, continuous monitoring pipelines, cannot wait 15 to 30 seconds per inference cycle. That's not a product. That's a proof of concept running in slow motion. Large context processing is slow. The bigger the window, the slower the first token latency. Hardware improvements help at the margin, but you're fighting physics. And if you want AI that actually operates autonomously in real time, which is the entire premise of agentic AI, you cannot build it on load everything, process everything, every time. Now, back to SubQ's subquadratic selective attention, because I want to be honest and precise about what it does and doesn't solve. Let's see this.
Today we're announcing a major architectural breakthrough, the world's first fully subquadratic LLM. SubQ has a 12 million token context window and frontier-level intelligence. It outperforms Opus 4.7 on long context at less than 5% of the costs. At 1 million tokens, SubQ processes tokens 52 times faster than flash attention, and dramatically changes the cost of training and inference, enabling us to scale context windows to 12 million tokens and beyond, pushing the boundaries of intelligence. This means your agents can now complete weeks of work.
SSA is a meaningful step forward. It's architecturally distinct from earlier linear attention attempts like RWKV or Mamba, which consistently showed long-range recall degradation on needle-in-haystack benchmarks. SSA's selective mechanism is more sophisticated than those approaches. But here's the important caveat: every subquadratic approximation I've evaluated trades something off. Sparse attention misses long-range dependencies. Sliding window attention loses global context. Every optimization makes a bet about what the model doesn't need to see, and that bet isn't always right. SSA appears to be one of the most promising approaches. But as of now, we don't have independent recall benchmarks on SubQ at 12 million tokens. We have their numbers, which are impressive. What I want to see: third-party needle-in-haystack at 10M plus tokens, recall degradation curves, and latency benchmarks on cold start inference. Until then, promising architecture, unverified at scale. That's my honest read. To be clear, I hope SubQ delivers. The field needs architectural diversity. But I evaluate systems by what I can verify, not what I can imagine. The real architecture? It isn't going to be a bigger chatbot. I think it's going to be something much closer to an AI operating system. For 1 second, imagine I gave you every email you've ever received, every Slack message you've ever sent, every meeting transcript from your entire career. And then I asked you one simple question. That's not intelligence. That's information overload. And I think that's the mistake the industry is making right now. We're treating larger context windows as if they're the destination. They're not. They're just one component in a much larger system. So here's the reframe I want you to carry out of this video. The industry has been asking, how big can we make the context window? The better question should be, how intelligent can we make the architecture around it? Because the future isn't one giant context window. It's an AI operating system with multiple memory layers. Layer 1, hot context. The live window. Small, fast, ruthlessly curated. Only what's needed for this specific reasoning step. Target, under 8K tokens for most agent tasks. Layer 2, episodic store. Recent conversation history, but not raw tokens. Structured summaries, compressed intelligently, with metadata for fast retrieval. This is where KV caching strategy matters most. Layer 3, long-term semantic memory. Vector stores, knowledge graphs, hierarchical indexes. Retrieved on demand. This is your RAG layer, but smarter RAG than most teams are building. Chunking strategy, embedding model choice, re-ranking, these aren't implementation details. They're architectural decisions that determine whether your system works. Layer 4, retrieval orchestration. This is the layer almost everyone underestimates. Most teams spend months choosing models. GPT or Claude? Gemini or open source? But the harder question is, What information should the model see right now? Because if you retrieve the wrong information, even the smartest model produces a bad answer. Retrieval orchestration is the decision engine that sits above the model. It decides what should be retrieved, which memory layer should it come from, how much context should be allocated, what should be summarized, what should be ignored, what should be forgotten. In other words, it manages attention before the model's attention mechanism ever runs. And that's why I believe retrieval orchestration is where intelligence increasingly lives. Not inside the model. Above the model. The model is becoming the reasoning engine. Retrieval orchestration is becoming the executive function. It's the part that decides what matters. And there's one more piece you won't see on most architecture diagrams. An explicit forgetting policy. Long-running agents need to continuously decide what stays in hot context, what gets compressed into episodic memory, and what can be safely discarded altogether. Because memory isn't just retrieval. Memory is retrieval and forgetting working together. A system that remembers everything eventually drowns in its own history. A system that forgets intelligently stays fast, focused, and scalable. And as models continue to converge in capability, I believe the biggest competitive advantage won't be who has the largest context window. It will be who builds the smartest memory and retrieval architecture around it. Anthropic, Google, and IBM are openly discussing this hybrid direction. It's not a fringe idea anymore. It's where production AI engineering is heading. And the teams that win the next 3 years won't be the ones with the biggest context window. They'll be the ones who build the most intelligent retrieval and memory orchestration on top of whatever window they have. So let me land this. 12 million token context windows are impressive. The engineering behind SSA is pushing the field forward. KV caching does make long context inference more practical than the naive math suggests. All true. But live context is not memory. Scaling context is not scaling intelligence. And brute forcing tokens without a memory architecture is not a strategy. It's a credit card bill waiting to happen. The real architectural moat over the next 3 years. Knowing exactly what to put on the table. And what to leave out. One question for comments: what's the biggest context or memory failure you've hit in production? Tell me the model, the context length, and what broke. I'll pick 3 answers to analyze in the next video. If this level of technical depth is useful to you, subscribe. Thanks for watching.